Okay, so let's talk a little bit about the hidden subgroup problem over a non-abelian group. Okay, so thus far we've only seen examples of HSP over abelian groups. We've seen Simon's problem, we've seen the simple period finding problem, and in the last lecture we saw the discrete log problem. So now let's talk a little bit about hidden subgroup problem over non-abelian groups. So this includes some very interesting problems. So the first example we have here is the graph isomorphism problem. Okay, so in this problem, we're given two graphs, and the question is, are they isomorphic or are they the same? Okay. So we have these two graphs here, are they the same? Well, what does that mean, right? What should it mean for two graphs to be the same? Well, one thing is you would think if two graphs are the same, they should have the same number of vertices. They should probably have the same number of edges. So that's the case for these two graphs. They both have 10 vertices. They both have 15 edges. But really to be the same, we'd want a stronger condition that the connectivity of these edges is also the same. Okay, so one way we can formalize that is to say that two graphs are isomorphic if there is a bijection between their vertex sets. So now we have two graphs, G1 and G2, and we want a bijection between their vertex sets. So that's just a one-to-one and onto a mapping between the vertex sets. So it basically just identifies a vertex in G1 with a vertex in G2. And we want this bijection to have the property that x comma y, so two vertices, x and y, in G1 form an edge in G1 if and only if their image under this bijection, pi of x and pi of y, form an edge in the second graph in G2. Okay, so that's the definition of an when two graphs are isomorphic. Okay, so in this case, actually, these graphs are isomorphic. Okay, so I've actually just given the labeling which identifies the vertices in the first graph and the second graph. So you should check that for any I and j, I comma j will be an edge in the first graph if and only if it is an edge in the second graph. Okay, so we can just check that for some random examples here. So let's take, for example, 10 and 5 are connected by an edge in the first graph. So in the second graph, yes, 10 and 5 are also connected by an edge. Here, 9 and 6 are connected by an edge in the second graph. And in the first graph, 9 and 6 are also connected by an edge. Okay, so you can go through that and verify that for all the edges, an edge is present in the first graph, if and only if it's present in the second graph. Okay, so that actually shows you that graph isomorphism is in a complexity class, which is called NP, non-deterministic polynomial time. So what that basically means is that if someone, in this case, if someone gives you the answer, right? So if someone tells you what the bijection is, so in this case, I've kind of given you what the bijection is with the labeling, then it's actually easy for you to verify that that bijection actually is an isomorphism. Okay, so it's easy in the sense that you can do that in time polynomial in the number of vertices of the graph, right? So basically what you have to do is just go through all possible pairs of vertices, this at most n squared pairs, and for each pair, check if it's an edge in the first graph, and then check if it's an edge in the second graph. Okay, so if those two are the same for all possible pairs of vertices, then then it is indeed an isomorphism. Okay, so so NP, we'll talk about complexity in the very last lecture, but NP is kind of thought to contain some hard problems. It's thought that to contain problems which cannot be solved efficiently. And graph isomorphism is kind of one of not very many problems that we know of, which is not one of the hardest problems in NP. It's not what we call NP complete, but at the same time, it's also not easy. So it's not known to be in polynomial time. Okay, so there's not a whole lot of problems that kind of sit in between these two things. And well, a few years ago, Babai actually gave a classical algorithm for graph isomorphism that runs in quasi-polynomial time. Okay, so that actually shows that, well, graph isomorphism, it's, you know, kind of almost in polynomial time. So it can be done with this quasi-polynomial time algorithm. So what does quasi-polynomial time mean? That basically means that the running time is something like n, oh, I grabbed the wrong pen. The running time is something like n to some constant power of log n. Okay, so something like that. That's quasi-polynomial time. Okay, so graph isomorphism is kind of a very interesting problem for these reasons. It's kind of intermediate between P and NP. It's not known to be in P. And it's also an example of a hidden subgroup problem. Okay. So a non-Abelian hidden subgroup problem, and hidden subgroup problem that we don't know how to solve efficiently quantumly, you know, in polynomial time. Okay, so let's see why graph isomorphism is a instance of the hidden subgroup problem. And we're actually going to start with an easier case of the graph automorphism problem. Okay, so what is an automorphism of a graph? Well, in this case, we're just looking for a permutation of the vertices, which preserves all the edges, which basically doesn't change the graph. Okay, so it's like you can relabel the vertices, and the graph looks the same. Okay, so formally, you know, for every edge in the graph, x comma y, when you look at the name of those vertices under the relabeling, so pi of x comma pi of y, that's still an edge of your graph. Okay. So I guess, you know, as a simple example, you know, if we were to take a triangle here, and if these are our vertices 1, 2, and 3, then if my pi sends 1 to 2 and 2 to 3 and 3 to 1, then that would be an automorphism of this graph, right? It would still just be a triangle. Okay. Okay, good. So the graph automorphism problem is to determine if a graph has a non-trivial automorphism. Of course, just the identity map is always an automorphism of a graph. But we're interested, you know, is there some other automorphism of the graph? And the set of all automorphisms, which I'm going to denote like this, aut of G, it's a subgroup of Sn, of the group of all permutations on n items. In this case, you know, n vertices. Okay, so how can we see that the graph automorphism problem is an instance of the hidden subgroup problem? Well, the function that we're going to look at is just, so it's a function that takes a permutation to a graph, okay? And for a permutation sigma, we just look at the graph formed by relabeling the vertices by sigma, okay? So that's our function. And we claim that this function hides the automorphism group, the group of automorphisms of the graph, okay? The subgroup of automorphisms. Okay, so to do that, we need to show two things, right? We need to show that F is constant on cosets of this subgroup, and we need to show that it's distinct on distinct cosets, right? Those are the two things that we need to show. Okay, well, constant on cosets, that's easy, right? Because if sigma is in the group of automorphisms, well, that means that sigma of G is just G again. Okay, so sigma 1 composed with sigma of G is just sigma 1 of G. Okay, and this holds for any sigma in the automorphism group. So that means that that this function is going to be constant on a coset of the automorphism group of G, right? Okay, because that basically that holds for any sigma in the automorphism group. Okay, on the other hand, let's suppose that for two different permutations, sigma 1 of G was equal to sigma 2 of G. Okay, well, that means that sigma 2 inverse times sigma 1 is going to preserve G, right? So if I just multiply both sides of this equation by sigma 2 inverse, then the right-hand side just becomes G. So that means that sigma 2 inverse times sigma 1 is in the automorphism group of G. Okay, so now what does that mean? Well, this is something that's in the automorphism group of G. Okay, so and sigma 2 times this is just going to be sigma 1, right? So that actually means that this here is in the coset sigma 2 times odd of G, okay? And of course, this is also, sigma 2 is in the same coset, right? Because the automorphism group of G, it contains the identity. Okay, so these two things are in the same coset. Okay, so what we've showed is that if sigma 1 of G is equal to sigma 2 of G, then sigma 1 and sigma 2, they must be in the same coset. Okay, so that means that if sigma 1 and sigma 2 are in the same coset, then they're going to map G to different graphs. Okay, so that means that our function is distinct on distinct cosets. Okay, so so that shows what we want to show, that this is indeed an instance of the hidden subgroup problem. So if you were able to solve the hidden subgroup problem over the symmetric group, then you could solve the graph automorphism problem. Okay, but we started talking about the not the graph automorphism problem, but the graph isomorphism problem. Okay, so let's go back to that. And essentially, the idea here of why the graph isomorphism problem is also an instance of the hidden subgroup problem is, if we're given a graph G1 and G2, well, we just build a bigger graph, okay, where the vertex set is the union, so the disjoint union of our vertex sets of these two graphs, okay? And the edge set is the disjoint union of the edge sets of these two graphs. Okay, and now what we do is we just look at the automorphism group of this new bigger graph, okay? And now if G1 and G2 are isomorphic, then there's going to be an automorphism that maps V1 to V2 and vice versa, right? V2 to V1. Okay, so if we can solve the automorphism problem of this graph and actually figure out what the automorphism group is, then we can just look at that group and see if there's an element of that group which maps V1 to V2 and vice versa. Okay. So this can be viewed as a hidden subgroup problem in S2n. Right now the size of the graph is 2n. And it can also be formalized as a hidden subgroup problem in a smaller, more specialized group. So this is called the Wreath product of Sn and S2, where basically you just limit the permutations so you have a permutation on V1, a permutation on V2, and then this B is just 0, 1, which basically means that if B is 0, then pi1 just acts on V1, pi2 acts on V2. But if B is 1, then pi1 actually acts on V2, and pi2 acts on V1. Okay, so in this case, you know, you just want to see if there's a permutation in this group which is an automorphism of G, and for which B is equal to 1. Okay, so it's flipping these two vertex sets. Okay, so graph isomorphism can be formulated as a hidden subgroup problem in this group. Okay, so let's talk about one other important special case of the non-Abelian hidden subgroup problem. So this is the Dihedral group. So the Dihedral group of parameterized by n is a group on 2n elements. And it's actually just generated by two elements, R and S. So the Dihedral group, you can think of it as the group of symmetries of a regular n-sided shape, like this, regular n-sided shape, n-gon. And what R represents is a reflection. So it's like a reflection about this middle line here. Okay, so the order of R is just 1. You know, because I'm sorry, the order is 2, right? Because if you reflect and reflect again, then you just acted as the identity. And the other element S is basically it's like a primitive rotation of this n-gon. So if I label the vertices of the n-gon like this, then S is basically a rotation by 2 pi over n, right? So it's going to send 0 to 1, 1 to 2, 2 to 3, etc. Okay, so the order of S is n, right? Because if I apply that operation n times, then I'll just be, you know, back where I started. I'll be sending 0 to 0 and 1 to 1, etc. Okay, so and the reflection and the rotation, they satisfy this relationship, and these are basically all the defining properties of the Dihedral group. So it's generated by two elements. One has order 2, one has order n, and they satisfy this relationship. Okay, so that's the Dihedral group. You know, quite a simple group, really. It's quite amazing that the hidden subgroup problem on this group is so difficult. So why is the Dihedral group hidden subgroup problem important? Well, it's closely related to the security of lattice-based cryptography. So, you know, as we've seen, Shor's algorithm can find the factors of integers efficiently and solve the discrete log problem. And, you know, a lot of cryptography that we use today is based on the hardness of those problems. So they would be compromised by, you know, a large-scale fault-tolerant quantum computer. So, you know, when people are looking for new public key cryptography protocols that are secure against quantum computers, a big candidate for that is this area of lattice-based cryptography. Okay, but if you were to find an efficient quantum algorithm for the Dihedral group hidden subgroup problem, then you know, that would break a lot of this new cryptographic schemes that are based on lattices. Okay, so this is actually you know, quite an important problem as well. So the best algorithm that we know of in terms of time for the hidden subgroup problem in the Dihedral group is due to Kuperberg from a few years ago. And he actually gave an algorithm that is sub-exponential time. So it runs in time like 2 to the order square root of log n. Yeah, and so that's the best we know. And, you know, this doesn't really impact the security of crypto systems yet. And this will also be, some people have chosen this for a project, so we'll actually hear more about that algorithm at the end of the course from one of the project presentations. Okay, so to finish this section, I just wanted to talk about, well, what is the difficulty in solving the non-Abelian hidden subgroup problem? So the difficulty is, is not actually in like implementing a Fourier transform over these groups. Like we know efficient quantum circuits for the Fourier transform over a lot of non-Abelian groups, in particular over the symmetric group and over the dihedral group. So that's not the problem. I mean, we can still produce a coset state, but the problem is basically, if we produce a coset state, how can we efficiently extract information from that state to identify the hidden subgroup? So you've seen that has kind of been the step that has varied the most, right? As we've seen these different algorithms, in the Abelian case, the period finding Simons, discrete log, kind of that, the quantum part of these algorithms is always the same, right? You produce this coset state to a Fourier transform and measure. And then what kind of varied was the kind of classical post-processing that you did to actually learn the hidden subgroup after that. So that seems to be kind of the bottleneck here, right? I mean, you could prepare a coset state, do a Fourier transform and measure, but then we don't know how to use that information, efficiently from a small number of samples to actually figure out the hidden subgroup. And of course, maybe you need to do something completely different in these cases, right? Okay, yeah, so that's it. I'll stop here.